We've got sort of a sequel to our last video, which was derivatives of power series, so naturally we would now want to talk about integrals of power series. So we talked about derivatives of power series, and that was really interesting. But for derivatives, we have a nice property that we can differentiate every function, which is something that's really cool. We've got the power rule, we've got the product rule, we've got the quotient rule, and we've got, most importantly, the chain rule. And then we have log, trig, exponential, and hyperbolic. We've got all those ways to differentiate functions. We can differentiate any function we want. It doesn't matter. We can use a combination of these properties and these derivatives that we memorized to differentiate any function we like, no matter how complicated. Integrals are a bit of a different story. We have all of these nice little rules here, but here we only have power rule and reverse product and reverse chain rule, so we've got substitution. And then we've got by parts, which is the reverse product rule. Unfortunately, integration is a more artificial construct that we've made to reverse derivatives, which is a little bit trickier. So we've developed techniques that we covered in techniques of integration, which was the trigonometric integrals, trig sub, partial fractions, Weierstrass. Then we've got a couple more in complex analysis, but that's for later. But essentially, we do not have the rules that we have for differentiation. So that's where power series really comes in handy, because if you remember, for the power series, we just needed to apply the power rule to one term. That was really easy. So we can do the same for integrals of power series, where we apply the power rule to one term as well. So sometimes it's easier to find a function and perform a transition to a power series and then take its integral, then find kind of a series solution to the integral. And oftentimes that's a lot easier than doing a lot of these methods, especially when you get into the more obscure techniques of integration. So let's get started by talking about the theory. Now, this is very similar to what we had the last time. So if we have a power series with a radius of convergence r, then the series is differentiable, thus integrable as well. So what this means is that if I want to take the integral of f of x dx, then I can also take the integral of the power series. Well, I take the integral of this guy with respect to x. And similar to the derivative, if I have an integral of a sum, we can also transform that into the sum of an integral. So we can take the integral of the parts in here. Obviously, 1 over 1, oh wait, yeah, we don't need this integral sign here. This is already the integral. Anyways, we get, if we take the integral of f of x dx, we take the integral of this guy. So we get the sum from n equals 0 to infinity. No need to go to n equals 1 because we've got an n plus 1 term of 1 over n plus 1 times c sub n, constant, times x minus a to the n plus 1th power. So this is just the power rule, or the reverse power rule. If I have an integral and I want to take the integral of x to the n dx, well, that is equal to x to the n plus 1 all over n plus 1. All right, so let's do an example. So I want us to integrate the following function. Now, it could be cool if this were on a Calc 2 final without just introducing this as a series question, but just as maybe an integral question. You would probably not know how to solve this integral. I mean, you could do a partial fractions of this. You definitely could do, I don't know about that. You might be able to do a partial fractions on this, and then that would be super messy. But, well, actually, no, you can't do a partial fractions on that. Anyways, you would not be able to do this integral. However, we can transform it into a series, and then that makes it a little nicer. So if you remember, our general power series is 1 over 1 minus x. So we have 1 plus x to the 7th in the denominator, but we can set u, we'll set u equal to x to the 7th. So we get the integral over 1, or we get 1 over 1 plus u. Now, how do we make this a minus? We get 1 over 1 minus negative u. So then we get 1 over 1 minus x to the negative 7th. I did this in a more speedy way, but we get the same thing. So if I want my sum, I can put this into the most general term for the series that we have for 1 over 1 minus x, as we found it a couple videos ago. But we get the sum from n equals 0 to infinity of -7, or negative x to the 7th times n, or to the nth power. So we can rewrite that as an alternating series. Of course, this makes things a lot easier when we perform an integral. So the integral of dx over 1 plus x to the 7th is equal to the integral of the sum from n equals 0 to infinity of -1 to the n times x to the 7n dx. Now we can do this integral quite easily because we can take the sum out, or we can take the sum out with this constant here, and we can just take the integral of x to the 7n dx, which is a trivial integral. N is a constant, 7 is a constant. We can use the power rule. So we get the sum from n equals 0 to infinity of -1 to the n times x to the 7n plus 1 over n plus 1. And if you remember from Unit 6 or Unit 5 or Unit 4, I don't remember which, you remember that we need to add the integration constant. So we get a plus c at the end as well. All right, so this actually marks the conclusion of our study of power series. In the next video, we want to look at Taylor series. So power series are very nice. They help us with a lot of elementary functions. However, Taylor series is a more general way of doing it. You'll see many parallels between power series and Taylor series. It's a type of power series. And there's a really nice formula, and it's really the capstone of your studies in Calculus 2. All right, thank you for watching, and we'll see you in the next video. Bye.